Here we are, the physics video lecture. Physics 203, video lecture 18. And we're working on Maupertuis principle. I think I'm gonna review the whole development there, and then we'll do a couple of exercises that I'll get us started on, and then I'll leave the rest to you guys. So there was a bit of a development to get there. And let's go ahead and just do it systematically again. So first of all, we're looking at action S equals integral L dt, but we're looking at now as a function of coordinates and time. So action as a function of coordinates and time. And so what we did originally, we had a t0, and so we had a point in space that corresponded to q0, t0, a point in configuration space, and then we follow the motion of the system out here to t, q1, t1, so t0 and t1, but this time, instead of it being a fixed boundary, we went ahead and let it be an open boundary. I'll ditch that there. And now that's how we come up with the idea, action as a function of coordinate and time being the upper boundary. So we get a couple of things immediately. I didn't do it in this order last time, but ds dt, of course, is just going to be L. That'll be your fundamental theorem, calculus. But if you vary S the way one does, that we did originally, you find that L dq dot at your upper bound here and so what we had out of this was ds dqi, it's an I, is equal to the piece of I. So we obtained these two relations. This one kind of just by construction, and this one looking a little deeper. Okay, and from that we were able to do the following. So ds dt would have been equal to sum over partial s partial qi dot, and outside of the sum, ds dt, okay, that would have been just s as a function of coordinates and time. Of course, with this thing here, that would be equal to L. Now this, on the other hand, sum of p sub I, q sub I dot, again, plus ds dt, equals L. And then we went back to our Hamiltonian, but H is equal to sum of p sub I, q sub I dot, minus L. So that this PIQI dot, there's a dot right there, is equal to H plus L. You got H plus L plus this partial equals L. And you get ds dt plus H is equal to 0. And that was this new differential equation that we're going to work our way towards solving. But we're not ready to solve it yet. But we did get something else out of this. I'll call that point 3 here. So now consider Hamiltonian systems where the energy is conserved. Then again, this thing right here, we can write as ds plus E dt is equal to 0. And we use that to get the new variational principle of Maupertuis. Because we then had 3, 4, I'll write integral sum of p sub I dq sub I is equal to 0. That followed out of this and the construction of this expression. And this was our new principle, okay, our new variational principle. It's, you know, it's not the same as Hamilton's principle, but of course it came from that. Now, we then had to express this, we had to rearrange it or eliminate all implicit time from this thing. And we finally arrived at, I'll do an intermediate step from E equals 1/2 double sum Aij of Q, Qi dot Qj dot plus U of Q. Okay. So we just went back to that standard energy that comes out of the Lagrangian. Double sum I and J. So we took this P sub K equals, yeah, well, I'm thinking of L and E at the same time. If I write this as L equals this minus U, let's go ahead and do that. Minus U. Then we have P sub K equals dl dq sub k dot. We express that in there. And then we eliminated all the dt from the entire expression, which are under the qi dot equals dqi dt. So we eliminated all of that and re-express this thing, and we'll leave this as L here. Remember, with a plus sign here, this is the energy, but not yet the Hamiltonian. It's the energy. Okay. So yeah, what did we finally get? I'll use this side of the board. We ended up with this variational principle. So the integral, we had the sum 2 E minus U double sum ij aij of q dqi dqj. So right now, still in general form, equals 0. And at this point, there really were just q's in here. Okay, no q dots, just q. Good. So now, and this is where we ended up last time, let q sub I equal q sub I of lambda, where lambda is just some parameter, okay, no longer the time. And then we go in here, qi prime, we're calling d qi d lambda. Yeah, now we get Moeller-Tui's principle in practical form, and that's what we're going to do a couple of problems with. So yeah, so now we have as our variational principle, keep numbering things, integral 2 e minus u. Now as far as this double sum aij of q, as far as that goes, we're going to see as soon as we implement this, we get this out of our kinetic energy expression. So that in every individual case. And then we would have a dqi d lambda, so qi prime, qj prime, and d lambda. So that's where that came from. This expression under the square root, or including the square root, this expression here is our f of q1, qn, q1 prime to qn prime. And for this we have Euler-Lagrange equations, because we have a variational principle equals 0, right? We have a variational principle, and we have something of this form, and that's why we have, first of all, we have two things. We have d lambda partial f partial q I prime minus partial f partial q I equals 0. And the other thing we have is Euler's second form, what we've, in Lagrange mechanics, what we've been calling the energy. But right now, it is going to be the sum of partial f partial qi prime times qi prime minus f. I equals 1 to n, f outside of the sum equals 0. So we're just back to the variational calculus for this problem, and what we were looking for was a formalism for conserved energy system, so that's a restriction, and one that will get us the equation of the trajectory. So we're not looking for the full dynamics now, we're looking for the trajectory. And there are two problems where we know that, or that we've studied, we know projectile motion and the Kepler problem, interesting trajectories, right? For the projectile, we know it's a parabola. For the Kepler problem, we get the ellipses. So we're going to apply this here, and I'll call this homework. We'll say use this whole business here, star, to solve projectile motion and the Kepler problem. And Kepler problem. Okay, projectile motion and the Kepler problem. So for both of these, we have to figure out what this aij of q is and set up the integral. So let's do it with the Kepler problem first. By which we mean the central force problem of this form. R dot squared, R squared, V dot squared, minus negative alpha over R, right? That was our U of R, Newton potential. So for this aij, so now I'm setting up this integral here, and let's see what we have. 2e plus alpha over r, right? Minus u plus alpha over r. Apparently I've got an M here. And then this aij of q, qi prime, qj prime. If we had we'll go ahead and do it as with a lambda first. So then we would have r prime squared plus r squared phi prime squared. Okay, that's it. Okay, that's it. The m, well, actually the m was part of it, but I pulled it out. Okay, and then we would have some d lambda equals 0. So variation of this. Good. So that's what we have. But we can simplify this some more to e plus alpha over r. You can see that m's going to drop out of the problem. It's not going to drop out of the problem. We'll leave it in there. Because if we drop it out, we'll lose something about the dimensions. Okay. Okay, so let's go ahead and think of it as dr d phi. Is that how I'm doing this? Consult. There are two options. Yeah. So if the r prime is dr d phi, then we have dr d phi plus r squared phi prime squared. So actually what we're doing is letting d lambda be equal to d phi. So we're going to end up with r prime squared as before, plus r squared, and this phi prime is d phi, so that comes, we have twice, and we have d phi outright. There we go. So let's put a red box around this one. Very important. R prime is dr d phi. So R prime is dr d phi. And this is going to get us, and not too long. Okay, good. This is going to get us to our solution of our problem pretty quickly. You have two ways of dealing with this. Namely, you could use the Euler Lagrange equation, and now we only have one variable. So let's go ahead and say, so here, f of, what do we have? F of r and r prime. No explicit phi. To e plus alpha over r prime squared plus r squared. So we have Euler Lagrange equation or Euler's second form. Prime, yeah. Use Euler's second form, which is this. To obtain a quadrature, and you're going to obtain one that you've seen before. So you take this into Euler's second form, you're almost done. Because since we've done that quadrature, what you'll do is you'll get Oh, good thing I caught this in real time. This one gives us a constant, right? When it's energy, conservation of energy, in this case, you're going to use Euler's second form, and the constant that you have there will be part of your quadrature. And you'll get a quadrature that you recognize from the Kepler problem. So you go back to your work on the Kepler problem and the integration that you guys did, you'll find that integral, and at that point you can declare victory, because we've done it before, okay? And the constant here, it'll be an interesting little discovery of what that constant actually means, because in the integral we've done before, we know what that constant means, and we'll then be able to identify it as the relevant constant here. So this is a great problem. To obtain a quadrature, yeah. You'll recognize that integral, put it into the same form as we did on the Kepler problem, and identify the constants of the quadrature. What is the meaning of the constant? Question mark. Okay, so you guys are going to enjoy that, because it's really only a few more lines off downstream from here. Okay. Good, so we'll do that. Now I want to also set up the projectile motion problem. These are both real convincers for this method here. Okay, so also, and this one we'll call just projectile motion. And again, setting up the Lagrangian for projectile motion, we're talking about half m x dot squared plus y dot squared minus mgy. Okay, so we're used to setting up projectile motion in the xy plane. And in fact, in the full generality, we launch from some y sub 0, with some initial angle and some v sub 0, and we get a parabola out of this problem. So we want to use Maupertuis's technique here to do that. So again, what we're looking at is this integral here, 2 e minus u. And then we could say we have m, I'll leave the m inside here this time, m x prime squared plus m y prime squared d lambda. So this would be the general form, but we're going to take the lambda as either x or y. So first of all, there's our principle. This thing under the root is the function we're looking for, except we got to choose a parameter. So let d lambda be equal to dx. Then what are we looking at here? Integral 2 e minus u. I could pull the m out. So now it's dx over dx squared. So that's just a 1 plus dy dx. So that's the y prime squared dx. And again, this is our, time for another red box. Yeah, red box. So this entire square root object is our function f. Yeah, so this is our f of, okay, we were actually concrete here, so let's be concrete with the potential energy E minus mgy minus mgy. So this is an f of y and y prime. Again, when you have something like this and it's one variable, Euler's second form is your best bet. So in terms of this one also, use Euler's second form. To obtain y of x. Okay, this one is fiddly. Okay. There's really nothing that difficult about it because the integrals are square roots or something to the 3/2. The integrals are all eminently doable. So you go past, you don't just get to the quadrature. Here you're going to obtain y of x completely. But there are a lot of constants up there, and it takes a while to make this one work. So what you can do to make this one work is work from the other end and make sure you remember projectile motion. So I'll help you with that by setting up what we know about projectile motion. Again, before I erase anything here. Your Euler's second form, your df dq prime, which is your df dy prime, times y prime minus the original f, which is the whole square root thing. And then you get a quadrature first, and the quadrature will have a constant in it, and then you try to do the quadrature to get y of x. So it's actually not that bad, but it's a little fiddly. So let's go ahead and I'll erase the Kepler side. I'll erase this side. And definitely good practice. Okay, definitely good practice. So I'm just going to put here recall for projectile motion. So suppose we're in here, we'll even have a y sub 0, just like my other picture. We've got a launch angle theta, we've got an initial speed v sub 0. Well, then we know that y of x turns out to be this. Well, you know what? I'm going to write it down. You guys should maybe even derive this just as a reminder. Y sub x, since we're starting right here, it's y sub 0 plus the tangent of theta times x minus g x squared over 2 v naught squared cosine squared theta. So that's what you get for the parabolic form of projectile motion. Basically, you solve for y of t and x of t, you plug one into the other. So this is what you get. What is the energy in this situation here? So you could let your energy, if you took the potential energy to be 0 here at the origin, when it's x and y axes, you could take your energy to be mgy sub 0. It's potential plus, of course, the kinetic energy, which is a half mv naught squared. It's also going to be interesting again what the physical meaning of that constant is. So don't get rid of any mass or anything. Make sure everything's dimensionally legitimate. You'll get the meaning of the conserved quantity in this, just as you're going to get it for the Kepler version. Those are both important insights. Okay. So yeah, that's what your energy would be. This here is your solution that you're working towards, right? But it's important to recognize this kind of thing here because your problem doesn't know anything about v sub 0, does it? Doesn't know anything about v sub 0, and as stated here, it doesn't know anything about E. And it doesn't know anything about theta. Okay, so those are actually things that you're going to identify as you go through it here. So v sub x is of course v sub 0 cos theta, v sub y is v0 sine theta. Yeah, you know, I'll even get started a little more on this one, just to make sure. Yeah. So yeah, these are all notes in terms of that problem right there. In addition, let's go ahead and construct df dy prime y prime minus f equals constant. Just so you see how that works. Right there we have, this is our function f, this whole square root thing. So we have, that's something to the 1/2 power, so we have 1/2 root in the denominator of that whole thing. And then 2my prime, actually a lot more than that. Okay. So we're doing with respect to y prime. Okay. So we have 2e minus mgy m 2y prime. Okay. And this whole thing here, 2e minus mgy m 1 plus y prime squared. Yeah. And then this y prime here gives us a y prime squared right there. And then we're subtracting off this thing here. And that is equal to some constant A. So when you do that, you're going to rationalize the same denominator. It's going to simplify quite a bit. And you're going to go from here to a quadrature. Now you've introduced this constant A as part of the problem now. Okay, so you go here to a quadrature. Don't lose any of these constants in order to make sure your dimensions stay good all the way through. Yeah, you know, we'll even do one more step. So 2e minus mgy 1 plus y prime squared. And an m. Take my own advice, right? M plus y prime squared. So we'll cancel this one against that one. And we get the common denominator, and you see we're subtracting off this 2e minus mgy times m, 2 minus mgy m. And we get the one with the y prime squared. So that simplifies enough. You do your separation of variables, and you just have square root type of expressions that can be integrated, no problem. So the quadrature is doable. There's just going to be a lot of constants and fiddling around. A lot of places to make errors, but it works. Okay. Good, so we have those two problems. That'll keep you busy. So I'll just add here as a note. simplify, and then bring it to a quadrature. And the integral is doable, very basic. And then eventually you'll figure out what this constant A was here, just like you'll figure out the constant that you had in your Kepler problem. And those will be interesting to find out, etc. Okay, so now we're moving on to what's called canonical transformations. Goldstein has a major chapter on this. We're going to touch on it lightly or thoroughly enough to get us into the Hamilton-Jacobi theory. So we'll spend a bit of time on it, but not too much. Above all, I want to show the whole motivation for this, because we're spanning a pretty large arc now in terms of theoretical constructs. Good, so I'm going to erase this. And we'll go back to the couple of things. But yeah, I'll write down first of all what the whole topic is called: canonical transformations. We want to develop reasonably systematically. Canonical transformations. Pretty much everything comes into play at this point on now. And all of this practice with the variational principles, variational calculus, is going to play a big role. Okay, so let's see. What's the best way to get going with this? Okay, we're going to go all the way back to, and it's good that we have these two problems up here, projectiles and Kepler. So the first thing to motivate what's going to be called the canonical transformation is the fact that we only solve our problems, it seems, if there's a cyclic variable. Okay, any problem with more than one degree of freedom, we hope to have some cyclic variables. So let's just start with reminding ourselves of cyclic variables, conserved quantities. So that's what allows us to solve a mechanical system. But you don't just have cyclic variables from the outset. You have to discover the coordinate system that gives you that displays the symmetry, because actually variables, conserved quantities, symmetries, that's what it all goes back to. But you don't necessarily immediately have the cyclic variable. It could be a situation where you would have to look for it. Okay. And that means you have to find an ideal set of coordinates. Okay. Ideal coordinate system for a given problem. Okay. So that's the first thing that's going on. And the examples, since we're looking at them, for projectiles, turns out that Cartesian coordinates are just the thing, Cartesian. And for central force, turns out that plane polar coordinates are just the thing. I may have done this before, I think I did. But if you were to reverse this, if you try to set up your projectile motion problem in plane polar coordinates, you're not going to be happy, okay? And if you try to set up the central force problem in Cartesian coordinates, you're not going to be able to solve it either. So the proper coordinate system is very important. Okay. So that's the first thing. Now, the next point is that Hamiltonian mechanics has more coordinates and therefore has a better chance of finding, or has a larger set of potential coordinate transformations. Okay. So Hamiltonian mechanics has a larger, and not just larger, much larger set of potential coordinate systems. And as we go through the theory, we'll see just how much larger the set of coordinate systems is. Because in Lagrange, you have what are called the point transformations, and you have Q1 to Qn for n degrees of freedom. In Hamilton, you have your Q1 to Qn and your P1 to Pn. Okay, so I have twice as many coordinates because P and Q, they all just function as independent coordinates, living in a phase space. So the transformations between sets of n and the transformations between sets of 2n are much different in magnitude. What we'll find is the most general transformation for this is just one out of basically an infinity of possibilities down here. Okay, so make sure I put the right words here. Potential coordinate systems and coordinate transformations. Okay. Good, so we have that. And my third point actually, since we're talking about transformations, I'll just add a note here. In Lagrangian mechanics, you're looking at transformation Q sub I is equal to Q sub I of Q1 to Qn, and T I equals 1 to n. That would be the most general transformation in Lagrangian mechanics. It's called a point transformation. Plane polar, Cartesian to plane polar, and back spherical polar would have been without the T, but you can in fact have a time-dependent coordinate transformation as well. So these are called point transformations. Now, in Hamiltonian mechanics, we're going to be looking at transformations like this. Your new coordinates, functions of the old coordinates, the old momenta, and time. And your new momenta functions, same as above here, Q1 to Qn, P1 to Pn, T. Okay. So there are just vastly more combinations, you could even say, in the space like this than there are in a space like that. Vastly more. So these are called point transformations. And we know how to do them. That's basically what we've been doing. these here are going to be called canonical transformations, and we're going to have to figure out the conditions to do this, which is what this chapter will be about. And then how to do this, and then how to solve problems. Let's see what else we have here as we set this up. Okay, so that was under point 2. Under point 3, I will say we're going to call this deriving Hamilton's equations from the variational principle directly. Okay, from a variational principle. Because we're going to be using this again. Okay, so it's going to, there you go. Okay, it's about the point transformation. So deriving Hamilton's equation from a variational principle, here's what we've done so far. We have variation L dt is equal to 0. Now what we're formally going to do is the following. We're going to write H equals sum over P sub I, Q sub I dot minus L. Solve for L here and plug it into here. Okay. So then we would have variation, right? If we substitute L, we have sum over P I Q I dot minus H. And we're going to write this Q1, I'll just write it as the vector. Okay. H of Q and P and T dt. So we're taking this alternate form of the Lagrangian. This assumes that you already, well, it assumes that we know that P sub I is dL dQi dot, which we do. Okay. Okay, what we have here is a function Q1 to Qn, Q1 dot to Qn dot, P1 to Pn, P1 dot to Pn dot, and T. Okay, that's all the variables in there. Although the P dots are not explicitly there. Nonetheless, we have Euler-Lagrange equations. If we have a variational principle, if we have this function, this integrand, then we have Euler-Lagrange equations for f. So Euler-Lagrange equations for f, equations for this function f, we would have, you see we're treating the Q's and P's as the dynamic variables, the Q dots, the P dots, same way. Okay, commas right here. So yeah, what do we have? D dt df dqi dot minus df dq Same thing for P. So dPi dot minus dF dPi is equal to 0. And let's see what happens. Okay, we have Q dots, P dots, right? Q and P, Q dot, P dot. So there are two n, I equals 1 to n, I equals 1 to n. Good, so how about here? dF dQi dot. We're going to get, and since I have I right there, we got to call something K. We'll do it right here. Use K just to not get mixed up there. K, that makes no difference. Okay. So now we'll pick these off. dF dQ K dot is piece of K, and we have a complete time derivative, d dt, piece of K, minus dF dQ sub K. Okay, the Q sub K is in here. Okay. Q sub K is in there, so it's minus a negative, that's plus dH dQ sub K is equal to 0. And on the bottom one here, we don't even have an explicit P sub K dot. Okay, there are no P dots in here, therefore this is 0, therefore dF dP sub K is equal to 0. But dF dP sub K is Q sub K dot minus dH dP sub K equals 0. And we now see from the first equation, we have P sub K dot equals minus dH dQ sub K, which we recognize as a canonical equation. And same thing right here. Q sub K dot is equal to dH dP sub K. So those are the canonical equations. So we derived Hamilton's equations from the original variational principle formulated in this manner, where we expressed L in terms of this minus H. And we're going to make use of that, but I think that'll be a good place to start next time. Now that we know we have this variational principle, in particular we see we can treat functions of the entire set of coordinates and momenta, okay? So that's not only 2n, that's 4n variables in a sense. Okay, let's see what time it is, I think. Yeah, this is a good place to draw a line. Let's see if I... Here's what I'm going to do. I'll just say a couple more words. Yeah. In fact, you know what? I'm referring to this thing right up here, so I'll just state our objective. Okay. So we have this greater possibility of transformations now. What we have to do is find the conditions under which such a general transformation still satisfies Hamilton's equations. Okay. That's what it means by them being canonical transformations. If you do a coordinate transformation like that, the question is, what are the equations of motion? Well, they should still be Hamilton's equations of motion, and everything we've done here we'll use to bring out the conditions for that. Good, so what makes a coordinate transformation canonical? What makes it satisfy Hamilton's equations? And with that, we'll leave it until next time. See you guys later.